Now that we've seen how coupled oscillations work for the specific example of masses and springs, we're going to use the Euler-Lagrange equation to treat more general coupled oscillations. So this is the Euler-Lagrange equation, and you've seen where this comes from previously in this course. We're not going to worry about where this equation came from anymore. We're going to treat it as some kind of magic trick that we can use to find equations that will solve problems. So we can sort of be ignorant while appearing to be utterly masterful. First example we'll look at is a mass, big M, sliding backwards and forwards here, pushed around by some springs, each with spring constant K. And attached to this mass is a pendulum that swings backwards and forwards. It's got length L, coordinate phi for the angular motion, and mass little m. Now, to use the Euler-Lagrange equation, we need to know the potential and kinetic energies associated with these two masses. The kinetic energy of this mass is pretty simple. It's a half big M x dot squared, so that's pretty straightforward. And the potential energy of this mass is just given by the potential energy stored in the springs, each of which contributes a half k x squared. So potential energy and kinetic energy of this mass are pretty straightforward. It's just the mass and spring problem. This one is a little more complicated, particularly the kinetic energy, because the velocity of this mass little m is not just the circular motion due to this pendulum, but it's also the motion of this mass moving backwards and forwards here changes the support point here, and so it's circular motion with an additional displacement in the horizontal direction. So to find the kinetic energy of this mass little m, we're going to have to break up its velocity into vertical and horizontal components. So the horizontal position is L sine phi, which is the horizontal component of the swinging motion, plus x, which is the coordinate of this mass big M up here. So that's the total horizontal position. The vertical position, if we take this position up here as being the vertical position equal to 0, then the vertical position we can write as negative L cos phi. So it's at its lowest point when phi is equal to 0, and when phi approaches 90 degrees, then we get a vertical position which is 0. So these are horizontal and vertical positions of this mass. So using these, we can go forward and find the kinetic and potential energies. The potential energy for this mass up here is a half k x squared from each of the springs, giving us a total of k x squared for this subsystem here. For the swinging pendulum, the potential energy is just the gravitational potential, so we just need to know its mass times gravity times height. The vertical position is negative L cos phi, so mass times gravity times negative L cos phi gives this potential energy here. The kinetic energy of this subsystem up here is a half m x dot squared, so that's relatively straightforward. The kinetic energy of the swinging part of the motion for mass little m is a half m, and then the total velocity of this mass squared. The total velocity of this mass squared is the horizontal velocity squared plus the vertical velocity squared. So the vertical velocity is the time derivative of its vertical position, and the horizontal velocity is the time derivative of the horizontal position. And adding these together, then we get the total kinetic energy. So this is quite complicated. This is the total Lagrangian then, T minus V, and from there we can compute. So we get an equation for the x coordinate and an equation for the phi coordinate. And so we have these two coupled differential equations. And they look mighty ugly. In the limit that the angle of this motion is very small, we can make some simplifications. You could actually feed these equations straight into Mathematica and it will solve the system for you. But if you want to see how the system behaves analytically, then we need to look at a small angle approximation. So making phi small, we can turn sine phi's into phi. So we can make the sine phi approximately equal to phi. We can also cross out anything squared or the product of two coordinates, because these nonlinear terms will be smaller than the linear terms. So we can cross out phi dot squared here, we can cross out x dot times phi dot, and we can make cos phi approximately equal to 1 here and here. Using these approximations then, we can find a much simpler set of equations. These are now linear equations for x and phi, and we can go further and write that in matrix form like this. So we have a matrix multiplying q double dot, where q is this vector containing x and phi, another matrix multiplying Q. So a matrix equation for Q, Q double dot, and Q the vector. This matrix equation doesn't yet look like the one we found for masses and springs because we've got matrices on both sides of this equation. Previously we had a Q double dot being equal to some matrix times Q. So we can go a little further by multiplying both sides of this equation through by the inverse of this matrix here. That will give us a pure Q double dot on the left hand side, and then we'll have an equivalent matrix equation to what we had in the cases of the masses and springs. So the inverse of this matrix here is given by this, which when multiplying both sides through by this matrix gives us Q double dot is equal to this matrix times Q. And now we can take this matrix and do the same trick as we did before. We can find values for the frequencies of the modes and the shape of the modes using the eigenvalues and eigenvectors.